Hello, everyone, and welcome to the presentation in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am Gary James.
And I am David Beams. And Gary, I am very curious about what results you're getting with that new vertical antenna in the backyard.
Well, David, I'd be happy to enlighten you as to how it's performing. Um, it has, I put down 32 17-foot radials for my ground plane, which is pretty much of a compromise from my first installation when I had the antenna at an old QTH. And but so far, the results have been really amazing. In the past week, I've been able to work a station, TX7L, in the Marquesas Islands in the Southern Pacific. And a couple days ago, I worked 4 Whiskey 8 X-ray on Timor-Leste, which is a DX position that is stationed there now for another couple of weeks. And the antenna has been performing very well. I set it up and adjusted it so that it would be resonant pretty much on the lower portion of each band. And I need to incorporate my tuner on 40 meters just to tune out a little bit of mismatch there. But on the other bands, I can run straight into the antenna without the tuner, and I'm 1.5 to 1 or less. So the antenna is working very well.
1.5 to 1 VSWR,
Yes.
standing wave ratio.
VSWR.
Okay.
Yes.
Dang. I was going to say that's a trapped vertical, isn't it?
No, it's
Really?
not trap per se. Yes, it's like a trap vertical, but the coils are exterior. Okay. And I think in terms of like a trapped Yagi, where they're enclosed in these cans,
Yeah.
when you see them on the elements, the HF6V by Butternut uses to form its resonant circuits, it has exterior coils and capacitors that are mounted around the central mast of the antenna.
Oh.
And the antenna is will perform on 6 different bands from 80 meters to 10 meters, including the work bands. So
Wow.
it's a nice little performer.
It's impressive.
Yeah, and so adjusting those coils, which allows you to move the resonant frequency up or down, is very easy. It's just a matter of loosening an adjustment nut on the end of the coil, sliding it up or down to move the resonant frequency. So very easy to adjust.
Wow. Well, I hope you have a lot of fun playing with it. I know you will.
I look forward to it. Yes.
So anyway, got one more example of the Beams op-amp analysis technique I wanted to show you.
Okay, well, let's continue with that.
All right, so let's see. Let me share the screen and get to PowerPoint, and there we go. Okay.
All right.
So this one I call to be continued. Yeah. There we go. It's what I call bonus circuits part 4 in analyzing the generalized impedance converter with the Beams op-amp technique. Now, if you haven't heard of the generalized impedance converter, I'll show you in just a moment. It's a real weird but really interesting circuit. But in case, just as a recap, the Beams op-amp analysis technique, something I came up with a couple of months ago. It's a simple method for analyzing all sorts of op-amp circuits, but I've never seen it in a textbook. And it's founded on or based on modeling the op-amp and its application circuit as an input voltage source V in and the op-amp and two linear networks, which I called A and B, that combine the input voltage and the output voltage and produce voltages at the non-inverting input, which I've labeled here V sub P because of the little positive sign, and the inverting input, which I call V sub N because of the little negative sign. And the relationships of these networks are that V sub P is equal to a weight A1 times the input voltage plus A2 times the output, and Vn is B1 times the input plus B2 times the output. And then I invoke the so-called virtual ground property or virtual ground criterion that Vp and V sub n are equal to each other. An op-amp that's connected with negative feedback will move its output voltage in such a way as to reduce the differential input, the difference between the two input voltages, to zero. And okay. And if I then set these two expressions equal to each other and then combine terms on opposite sides of the equation, little manipulation with algebra, very simple algebra, I got this transfer relationship. V out to V in is A1 minus B1 divided by B2 minus A2. So if I can find these weights A1 and A2, then I can find the transfer relationship of the op-amp circuit from those coefficients. And it has an amazing range of applications, or at least it seems to. And this one I want to apply to this circuit called the Generalized Impedance Converter. Now, the Generalized Impedance Converter is this really weird looking circuit. It consists of two operational amplifiers and a chain of 5 impedances, series connected chain of 5 impedances like this. And here's the input voltage to this network. And the input impedance is the ratio of the input voltage to the current that flows out of that source into the network. Now, okay. Since this operational amplifier, we assume that the inputs of the op-amps are open circuits. They don't draw current. So all of the input current must turn the corner and flow through impedance Z1. So that means that the input current, I can calculate that as the input voltage minus the output voltage of this op-amp, U2, divided by Z1. Okay. And if I can find VO2, the output voltage of op-amp 2, if I can find that in terms of Vin, then I can get a unified expression. I'll click too soon. I get a unified expression for the input or the input impedance of this network. That's where I'm going with this thing. So let's apply the technique. We're going to pull op-amp 2 out. We're going to leave op-amp 1 in. It's part of the network, and I've got one network that's going to provide both the A and the B coefficients here. Okay. So pulling op-amp 2 out. The network for A1 and B1, we apply the input voltage while the output voltage of op-amp 2, VO2, is forced to 0. And here, I can read the coefficient B1 right off the circuit diagram because op-amp U1 it's still an active device, and it's going to force the voltage at its inverting input Vn1 to be the same as Vp1. So you see Vn2, voltage at the inverting input of op-amp 2, which is the same as the voltage at the inverting input of op-amp 1 because they're tied together. And this op-amp forces that voltage to be the same as the input. So the coefficient B1 is just simply 1. If you know the virtual ground property of the op-amp, you can read it right off the schematic diagram. Okay, so now the current that's flowing here in I2, as I've labeled it, it's minus Vn over Z2 because the voltage here is the same as the input voltage. Again, that's the virtual ground criterion of op-amp 1 at work.
Mm-hmm.
But that none of that current flows into the op-amp, so that entire current must flow through Z3, and that lets me calculate the output voltage of op-amp 1. It's V in minus Z3 times I2, or expression V in times 1 plus Z3 over Z2. But now I'm looking for VP2, but VP2 is just a voltage divider off of VO1, which I already know. There's VP2 and there's the voltage divider. So I have VP2 as a function of Vn. There's my A1 coefficient. So I've got A1 and B1.
Okay.
Okay, so now what I'm going to do is I'll take that same network, but I'm going to put a voltage at VO2 and force Vn to 0. And here we've done that. Put the voltage, the output voltage VO2 on, Vn at 0. And I can read the coefficient B2 right off the schematic diagram again, because since voltage VP1 is held at 0, this op-amp will hold the virtual ground at Vn1. So Vn2, the ratio of Vn2 to VO2 is 0. Because no matter what voltage I force here, that's always going to stay at 0. Okay, so
Yep.
that one was easy. Then the current I2 is VO2 divided by Z2. Since this is held at a virtual ground, the current is just simply this voltage minus 0 divided by Z2. And this is 0 at Vn1. The same current I2 is flowing through Z3, so it's easy to calculate that VO1 is minus Z3I2. And again, VP2 is just a voltage divider off of the output voltage of op-amp 1. So there's the A2 coefficient. Actually,
Okay.
pretty straightforward stuff.
Mm-hmm.
Okay, so then
Okay.
I've got all the 4 coefficients, and I just combine them. And VO2 to Vn turns out to be Z3 Z5 minus Z2 Z4 over Z3 Z5. Okay, we're actually getting close to the end of this. Since I can find the input current as Vn times 1 minus VO2 over Vn divided by Z1, then just substituting this for VO2 over Vn, there I have In and Vn, and there is the input impedance of this entire network. Mm-hmm. And it's Z1, Z3, Z5 over Z2, Z4. That's what I calculated from my method. And I know that, happen to know that this is a known result. So,
okay.
Got it. Now, here's the interesting thing. What I find fascinating. If I let either Z2 or Z4 be a capacitor, what does the overall input impedance of this network look like? Are you thinking it looks inductive?
Yes, yeah. I believe it would.
It would be. Yes. So you see what happens, what I can do with this circuit is if I let either impedance 2 or 4 be a capacitor and the rest be resistors, this circuit behaves as if it were an inductor, a synthetic inductor. Okay,
very
so
interesting.
I put up a synthetic inductor as a bonus circuit that you can download. I call it bonus circuit number 11. It's that LTSpice file. And one interesting benefit of this topology is that the output voltage at VO1 is the same as the voltage across the inductor, but it's buffered. It has a low impedance output, and it has a voltage gain of 2. Okay. So then bonus circuit number 12, which is also available for download, is a bandpass filter that uses a generalized impedance converter for a synthetic inductance. So here's the synthetic inductance. There's the parallel resonating capacitor. There's the resistor. This circuit has a resonant frequency at 10 kilohertz and a Q of 10. And
Okay.
you can download it and run it with LTSpice and try it yourself.
Okay.
Okay. Oh, it gets better. It gets better. Here's bonus circuit number 13. Now, I have a bandpass filter that has more than unity gain, greater than unity gain. And if I were to take the output of the bandpass filter and feed it back into the input, I can make a self-sustaining oscillator.
Okay.
Okay. And I take some of the output voltage, feed it back to the input, and I have a couple of diodes here for amplitude limiting. And the only other odd thing in this circuit is I have this little pulse voltage source, which is just a little kickstart to get the oscillation started. It's only needed for simulation purposes. In the real world, you wouldn't need it. But and bonus circuit number 13, this bandpass filter oscillator. And one more. Yes, there's more. This is the same bandpass filter oscillator, but well, let me delve into this. This is the same voltage I've labeled Vin before. This is the input of the synthetic inductor. This voltage is twice Vin, and the voltage VO2, okay, if both of these if impedances 4 and 5 are both resistors and they're both equal in value, and if the capacitive reactance of C2 is equal to the resistance of R3, then the output voltage here, VO2, is equal to Vin plus JVin. The J represents a 90-degree phase lead. And then I can combine 2Vin, the output here at this op amp, with, well, I have this difference amplifier. VO3 is twice VO2 minus VO1. And the net result is I get 2JVin as the output voltage. So I have 2Vin here and 2JVin here. In other words, the output of VO3 has the same amplitude as VO1, but it leads it by 90 degrees. So this makes a so-called quadrature oscillator, which provides both sine and cosine outputs simultaneously. That's bonus circuit number 14. And I'll just show you here. This is a simulation of that circuit, and the yellow trace is VO3, and you can see it has pretty much very close to the same amplitude as VO1, and it's leading it by 90 degrees, providing quadrature outputs. And for anybody who wants, you can download these circuits and play with them.
Well, quite interesting, David.
So,
and I would say you have come up with a very unique way of looking at the op amp and the circuitries with your method.
Like I say, it won't make me rich, but
but it provides some insight. So thank you.
All right. So anyway, if anybody's wondering, oh, yep, our predictions come true. We are good. Okay, so just to wrap everything up here, the link for these bonus circuits is in the description of the video. And you can follow the link and you can download those circuits. You can download the PowerPoint too, if anyone's interested. And if you find these resources useful, well, we'll always take cash. But favorable reviews would be, we'll take those too.
There you go.
So, my friend, as we always say, we appreciate your visiting to our viewers. We appreciate your visiting with us. Keep those cards and letters coming. That's a dated expression, but so are we.
Well, and also an on-air expression, good DX.
Yes, and good DX to you too, my friend. Gary, thank you for your time, and we'll be talking to you again soon.
Okay, you're so welcome, David. Look forward
Okay.
to our next encounter.
All right. Take care, my friend.
Okay.
And let me figure out how to stop the recording. There it is. Okay. Take care, Gary. Bye-bye.
Very good, David.